Okay, let's unpack this. You've shared some truly incredible material on a topic that's, well, actively shaping our future. How artificial intelligence is revolutionizing the management of essential natural resources.
It really is.
This deep dive is all about giving you a shortcut to being well-informed, packed with surprising facts and insights. Our mission today is to cut through the complexity and reveal how AI is rapidly becoming the indispensable intelligence layer for everything from discovering new oil fields to orchestrating smart electrical grids.
And what's crucial to understand right from the outset is that the 21st century presents us with this kind of dual challenge.
Right.
Escalating demand for resources, but alongside that, an urgent need for sustainable management.
Absolutely.
And, well, traditional methods are simply not keeping pace. This material really highlights how AI offers a transformative toolkit.
A toolkit.
Yeah, allowing us to navigate immense complexity, anticipate disruptions, and optimize operations with just unprecedented precision. It's truly a strategic shift.
Absolutely. And when we talk about AI's power, I mean, at its core, it's about its unparalleled ability to process these vast quantities of data and discern patterns that are often, well, imperceptible to human analysis. This is where the magic begins, really.
Precisely. It's like equipping ourselves with a super-powered magnifying glass. One that can see connections no human eye ever could.
Exactly. And to understand how it does that, let's talk about the three core learning paradigms. They're essentially different strategic approaches to problem solving, dictated by the kind of data you have.
Okay.
First up is supervised learning. Think of it like a student learning from a textbook that has a complete answer key.
Okay, makes sense.
The AI is trained on these labeled data sets, historical information, where we already know the correct outcomes. It then learns to map inputs to those known outputs.
So if you're trying to predict something specific, and you've got tons of historical examples to learn from, this is your go-to.
Exactly. For instance, it's used for prediction, like forecasting continuous numerical values. Imagine predicting future electricity demand by feeding the AI historical temperature and consumption data.
Right, classic example.
Or for classification, which is assigning inputs to predefined categories. A utility company might use it to classify an energy purchase as, say, normal or potentially fraudulent based on past transactions.
What's powerful here is how readily the electricity sector, for example, can leverage this. I mean, they have decades of meticulously labeled historical data consumption, pricing, weather.
Yeah, tons of it.
It makes it exceptionally well suited for supervised learning to forecast future demand. That's a massive advantage for them.
Definitely. Then there's unsupervised learning. This is more about discovery in the unknown.
Okay.
It operates on unlabeled data, meaning the AI finds hidden patterns or groupings without any prior knowledge of what those groups should be. It's like giving a detective a box of clues and just asking them to find the connections themselves.
So instead of being told what to look for, the AI kind of figures it out on its own. What kind of hidden connections does it typically uncover?
Well, a key application is clustering, where it groups similar data points together. Imagine segmenting millions of energy consumers into groups like nighttime chargers or weekend peak users without ever telling the AI those categories exist.
Okay. So it finds the structure.
Exactly. Helps optimize grid load. Or, crucially for resource management, anomaly detection. This is about identifying rare observations that deviate significantly from the norm. These outliers are often critical indicators.
And that's where it shifts, right? From just grouping data to actually flagging potential problems.
Precisely.
So if you have a brand new sensor on, say, a mining vehicle, constantly generating data you've never seen before, unlabeled data.
Right.
Unsupervised learning is really the only viable initial approach to detect those subtle deviations that might signal an impending failure.
It's spotting the needle in the haystack.
Yeah, without even knowing what the needle looks like first.
Exactly.
Yeah.
And finally, we have reinforcement learning. This is learning through interaction and real-time feedback. An AI agent takes actions in a dynamic environment, observes the outcomes, and receives rewards or penalties.
Okay, so trial and error.
Through this iterative trial and error, it develops an optimal strategy.
This is where the AI truly starts to act and make decisions in complex, changing situations rather than just predicting or classifying.
Exactly. For example, an agent could manage a smart grid, dynamically deciding when to store energy, draw from renewables, or purchase power to ensure stability and minimize costs.
Constantly learning.
Or in mining, it can optimize routes for autonomous hauling trucks, maximizing efficiency and minimizing fuel consumption in a dynamic open pit environment, constantly learning from every decision.
When we connect this to the bigger picture, the choice of AI strategy isn't arbitrary, is it?
Not at all.
It's fundamentally dictated by the nature of the data you possess and your specific objective. An organization's, let's say, data maturity directly shapes its AI capabilities.
Right.
It guides those strategic investments in data collection and labeling.
So now that we've laid out these strategic approaches, let's talk about the computational engines that power them. Neural networks and deep learning.
Okay.
Inspired by the human brain, they consist of interconnected layers of neurons that process information, learning intricate, nonlinear patterns. Deep learning, with its many hidden layers, performs something called hierarchical feature learning.
And what's really transformative about that hierarchical feature learning is how the initial layers detect simple patterns, while deeper layers recognize increasingly complex concepts. Think about recognizing a specific geological formation or a nuanced seasonal demand cycle.
Yes, and this ability to perform automatic feature extraction is truly groundbreaking. Instead of human experts painstakingly selecting and transforming raw data into usable variables.
Which takes forever.
Right. Deep learning models learn the most salient features directly from raw, unstructured data. For example, a convolutional neural network or CNN.
Right, those are used a lot with images.
Exactly. It doesn't need to be explicitly told what a geological fault line looks like in a satellite image. It learns to identify the relevant textures and shapes on its own. This dramatically scales the potential for new discoveries.
And it essentially allows the AI to discover new indicators that human experts might not have even thought to look for. It's pretty amazing.
Totally. When it comes to real-world applications, recurrent neural networks, and especially long short-term memory networks, or LSTMs,
LSTMs, yeah.
they're designed for sequential data where order is critical. They have an internal memory, making them incredibly powerful for time series analysis, forecasting electricity demand, or predicting commodity price movements.
And these powerful architectures, combined with those core learning paradigms we talked about, they enable two paramount techniques for effective resource control: time series forecasting and anomaly detection. These are really two sides of the same coin when it comes to understanding and managing dynamic systems.
Absolutely. Time series analysis and forecasting is the cornerstone of everything from demand planning to inventory management and price prediction. It involves breaking down historical data into its components. The long-term trend, seasonality, like predictable summer AC demand, cyclical patterns, often tied to economic cycles, and irregular components, the unpredictable noise.
All the ups and downs.
Exactly. While classical statistical models exist, modern AI models, especially LSTMs, excel at capturing complex, nonlinear relationships. They incorporate external variables like weather forecasts or economic indicators.
Right, bringing in more context.
Leading to significantly more accurate forecasts.
And on the flip side, anomaly detection is about identifying those data points that just don't conform to an expected pattern.
The outliers.
Exactly. In critical infrastructure, these outliers are often powerful early warnings of significant events.
They can be a single extreme spike or maybe an observation that's only unusual in a specific context, like, unusually high heating oil demand in July.
Right, context matter.
The strategic value is immense. It enables a shift from reactive maintenance, where you fix things after they break.
Which is costly.
Very. To a truly predictive one fixing before a break, saving massive costs and preventing downtime. It can even detect electricity usage indicative of theft or unusual network traffic signaling a cyber attack. It's all about spotting what doesn't fit. We've just seen how incredibly powerful these deep learning models are at finding patterns and making predictions. But here's where it gets really interesting. Maybe a little tricky. They often operate as black boxes. Their internal decision-making logic can be completely opaque, even to their creators.
Right, the black box problem. And this raises a crucial question, doesn't it? When an AI system recommends, say, a multi-million-dollar investment or it advises shutting down critical infrastructure, why should we trust it without understanding its reasoning? In essential resource management, interpretability isn't a luxury. It's a fundamental requirement for accountability, safety, and, well, continuous improvement.
So what are the real-world consequences if, say, an AI managing a mine's safety systems makes a recommendation that nobody can truly understand or verify?
Well, there are several critical risks. First, there's a fundamental lack of trust and adoption. Human experts are unlikely to fully trust recommendations they can't understand, especially when the stakes are high.
Right, they'll just ignore it.
Exactly. An unexplained prediction of equipment failure might simply be ignored, negating the system's entire purpose. Second, it leads to a failure to debug and improve. If a black box model makes an incorrect prediction, it's nearly impossible to diagnose the root cause.
So you can't fix it.
Right, you can't fix it, preventing improvement and leaving the system vulnerable to repeated suboptimal outcomes. And finally, there are significant regulatory and compliance hurdles. Regulators are increasingly demanding transparency in AI decision-making, particularly in sectors affecting public safety and the environment.
Makes sense. This urgent need for clarity has given rise to explainable AI.
XAI.
A suite of techniques designed to make AI models transparent, interpretable, and trustworthy. These techniques don't necessarily simplify the model itself, but they provide clear, post-hoc explanations for its behavior.
Kind of lifting the lid on the black box.
Exactly. Let's look at two key XAI frameworks with some real-world examples. First, there are model-agnostic methods. These are powerful because you can apply them to any type of machine learning model.
Okay.
Think of them as universal translators for AI.
So it doesn't matter if it's a simple model or a complex, deep neural network, these methods can shed light on its decisions.
Precisely. A great example is LIME, which stands for Local Interpretable Model Agnostic Explanations.
LIME. Okay.
So if an AI flags a specific wind turbine for an urgent maintenance check, a maintenance engineer can use LIME to get a targeted explanation for that individual prediction.
Specific to that one turbine.
Yes. The explanation might show the prediction was driven by, say, vibration frequency in the 50-60 Hz range increased by 15%, and gearbox oil temperature is 8 degrees C above the 24-hour average. This gives a clear, actionable rationale.
That's incredibly powerful for building trust at the operational level.
Yeah.
It moves from the AI says so to the AI says so because.
Precisely. Another powerful one is SHP, or Shapley Additive Explanations. This is a more sophisticated approach. It calculates the contribution of each feature to pushing a model's output away from a baseline value.
Quantifying the impact of each factor.
Exactly. Imagine a logistics AI recommends rerouting a lithium shipment via a longer, more expensive route. A SHP force plot could visually show that high probability of labor strike at original port, predicted 12-day customs delay, and critical inventory level at destination factory overwhelmingly counteracted the shorter shipping distance. SAP quantifies this impact, making it crystal clear the model prioritized avoiding a costly stockout.
What's truly fascinating here is that XAI extends beyond simply building trust or debugging. It transforms AI into a partner for genuine knowledge discovery.
How so?
Well, when XAI reveals a model relying heavily on a feature human experts previously considered unimportant, it prompts the crucial question, why?
Right. Why is that important?
Exactly. This can lead to investigating underlying processes, potentially uncovering new scientific indicators, or revealing unexpected correlations that lead to a deeper understanding. It refines both the AI model and the domain expertise itself. It's a feedback loop for learning.
That's a great point. So the theoretical capabilities of AI find their true value in practical application. Across the spectrum of essential natural resources, AI-driven pattern recognition is enhancing efficiency, improving safety, reducing environmental impact, and securing supply chains. It's fundamentally moving resource management from reactive to proactive and predictive.
Where the real impact happens.
Let's start with the energy sector, which is, as we said, a prime domain for AI. For fossil fuels like oil and gas, AI is revolutionizing exploration and reservoir management.
Yeah, it's no longer just about geologists poring over maps. AI can analyze massive geological and seismic data volumes to identify subtle patterns correlated with hydrocarbons, generating these high-probability prospectivity maps.
That's right. There was a notable success, I think, in the North Sea, where an AI platform analyzed over a decade of historical drilling data to identify a new field consistently overlooked by human geologists, led to a significant increase in reserves. And for predictive maintenance, AI systems continuously monitor real-time data from thousands of sensors on drilling rigs, pumps, pipelines, you name it.
all that sensor data.
They learn normal operational signatures and use anomaly detection to flag minor deviations.
We saw this on an offshore rig in the Gulf of Mexico, where an AI system successfully predicted a critical valve failure weeks in advance. Weeks! That prevented a major operational shutdown and a huge safety hazard. This proactive approach significantly reduces unplanned downtime and can even prevent catastrophic failures like oil spills.
It's absolutely game-changing. Now, let's talk about electricity and heat. The electricity grid is arguably the most complex machine ever built.
It really is.
And AI is becoming its indispensable intelligence layer.
Indeed. For smart grid management, AI acts as the central nervous system, real-time monitoring and control. It can automatically detect faults, reroute power to prevent widespread outages, balance load. It even helps detect anomalies that could signal electricity theft or equipment malfunction.
And for demand forecasting, which is so critical for matching generation with consumption, AI-driven models consistently outperform traditional methods.
We touched on this.
Yeah, they process a multitude of variables, historical consumption, real-time weather, economic indicators, even public events, to predict demand with remarkable precision.
And this precision is what allows for the seamless renewable energy integration we need, right? AI accurately forecasts the variable output of solar and wind from weather data and satellite imagery. This enables grid operators to proactively manage resources, scheduling large-scale batteries to charge when generation is high and discharge when low.
So you get reliable supply.
Exactly, ensuring reliable supply and reducing reliance on those expensive, often dirty, fossil fuel peaker plants.
And predictive maintenance isn't just for oil rigs. For critical assets like turbines and transformers, AI can predict failures before they occur. The International Energy Agency reports that AI-based fault detection can reduce outage duration by 30–50%.
That's significant.
Huge. The energy company AES, for example, implemented an AI system for its wind turbine fleet and achieved over 90% accuracy. Saved millions and significantly improved power delivery consistency.
Impressive results.
Moving beyond energy, let's explore critical materials. These are essential for modern economies and, crucially, the green energy transition.
Yeah, think lithium, cobalt, rare earths.
Exactly. This includes metals and minerals. Here, AI is a powerful tool for exploration and prospectivity mapping. It processes vast and diverse data sets, satellite imagery, geophysical surveys, geochemical analyses, to identify geological patterns indicative of mineral deposits.
Patterns humans might miss.
And deep learning models can actually detect subtle alterations in surface geology associated with underlying ore bodies. This drastically increases drilling success rates and reduces exploration costs.
Makes exploration more efficient.
Hugely. For mining optimization, AI enhances efficiency, safety, and sustainability right on the ground. Geospatial analysis helps identify geological hazards.
It's important for safety.
And autonomous drilling rigs and haul trucks, guided by AI and GPS, can operate 24/7 with greater precision.
What's also fascinating is AI's role in managing resources within mining operations, like predicting optimal amounts of water needed or enabling real-time environmental monitoring, like tracking tailings dam stability. It's a holistic approach.
Absolutely vital. And then there are batteries. The exponential growth of electric vehicles and grid-scale energy storage has created just unprecedented demand. AI is critical for managing this sector sustainably.
This is where supply chain management becomes incredibly complex, isn't it?
Totally.
AI models forecast demand, monitor supply chain risks, and optimize logistics for critical materials like lithium and cobalt, which are often geographically concentrated and politically sensitive.
Big geopolitical factors there.
Definitely.
And for life cycle and recycling optimization, AI is crucial for achieving a circular economy for batteries.
Which we desperately need.
We do. AI-powered systems using computer vision can automatically identify and sort different types of used batteries from mixed waste streams with high speed and accuracy.
Sorting the chaos.
Exactly. Once sorted, AI analytics optimize chemical and metallurgical processes for material recovery, maximizing the yield of valuable metals that can be reintegrated into the production supply chain, reducing the need for new mining.
Closing the loop.
What's truly remarkable, though, is the universal power of these AI techniques. They are fundamental tools for pattern recognition, prediction, optimization. Their significance is revealed by their efficacy across a vast range of seemingly unrelated domains.
Right.
The same AI that predicts oil prices can also predict human choices.
That's the real aha moment, I think. It's not just about silicon chips or algorithms. It's about a core computational capability to find patterns in any data, no matter the source or what it represents.
Precisely. Let's look at the human element, recognizing patterns in society. In behavioral economics, businesses use AI to predict consumer behavior. They analyze purchase histories, web browsing, social media.
All that digital footprint.
Yeah, recommendation engines and dynamic pricing models adjust prices based on predicted demand. It's directly analogous to how utility companies forecast energy demand.
And in politics, AI, particularly natural language processing, analyzes millions of social media posts, news articles, speeches.
Sensing the public mood.
Exactly. Gauging public opinion in real time, forecasting election outcomes, tailoring campaign messaging. It's a mirror image of how AI analyzes thousands of sensor readings to understand the overall health or sentiment of a complex industrial asset.
That's a fascinating parallel. During the COVID-19 pandemic, AI models in public health predicted virus spread by analyzing mobility data, case reports, health records.
Yeah, that was crucial.
Enabling authorities to optimize allocation of scarce resources like hospital beds and vaccines, a direct parallel to AI-driven supply chain management for essential materials.
Resource allocation under pressure.
And in education, AI-powered personalized learning platforms track student progress in real time, adapting curricula with customized content and resources to suit individual learning paces and styles. This dynamic optimization of educational resources for each student is conceptually identical to optimizing water or fertilizer application for each plant in a field.
Tailoring resources to individual needs.
AI also helps in decoding complex systems in the natural world. In biology and genomics, deep learning models like Google DeepMind's AlphaFold recognize patterns within vast biological data, predicting how genetic mutations impact gene regulation, helping pinpoint causes of genetic diseases.
Unlocking biological secrets.
It's analogous to AI sifting through terabytes of seismic data for the faint signature of a mineral deposit.
And for environmental systems and climate change, AI is absolutely essential for monitoring planetary health. CNN's analyze high-resolution satellite imagery to track deforestation, coral reef health, illegal fishing.
Eyes in the sky.
Basically. AI processes enormous data sets to improve climate projections and forecast extreme weather events like hurricanes and wildfires with greater lead time. It's giving us a clearer picture of our planet than ever before.
So, how do all these seemingly disparate applications tie together? The global food supply chain serves as a perfect, comprehensive case study. It demonstrates how various AI techniques can be integrated to manage a critical resource system efficiently, safely, and sustainably.
This is where we see the full breadth of AI applications really come together, right? In precision agriculture, drones and satellites capture farm images. AI-powered computer vision assesses crop health, identifies stress from pests or disease, measures soil moisture.
Getting very granular.
Very.
This allows precise, targeted application of water, fertilizers, pesticides, potentially reducing chemical usage by 25–50% while maintaining yields and reducing environmental runoff. Huge potential there.
Definitely. Then, in production and processing, AI-driven machine vision systems perform automated quality control on production lines, grading fruits and vegetables, detecting defects.
Faster and more accurately than humans.
Often, yes. With superhuman speed and consistency. Anomaly detection monitors processing equipment to predict maintenance needs, too.
And for traceability and safety, AI, often paired with blockchain technology,
Right, the ledger.
creates an immutable digital ledger tracking food products from farm to table. This allows for rapid digital recalls, pinpointing contamination sources in hours rather than weeks.
That's a massive leap in food safety. Hours versus weeks.
It really is. And finally, for supply chain optimization, AI tackles food waste by providing far more accurate demand forecasting. It analyzes historical sales, weather patterns, holidays, even social media trends.
Try and predict what people will buy.
Exactly. This optimizes inventory management, reducing overstocking and spoilage. AI also calculates the most efficient transportation routes, cutting fuel consumption and ensuring freshness of perishable goods.
The food supply chain is really a microcosm of AI's universal power, isn't it?
It seems so.
It shows how these tools, initially discussed for oil or metals, are fundamentally about understanding and optimizing any complex system, no matter the domain.
So, what does this all mean for the future? The integration of AI into natural resource management is clearly a profound strategic shift. While the potential for unprecedented efficiency and sustainability is immense,
Huge potential.
realizing this positive future is not guaranteed.
No, definitely not.
There's a critical concept here, the sustainability paradox, the environmental footprint of AI itself.
This is a vital conversation to have. Because, on one hand, the computational power needed for large-scale AI models is just immense.
Right.
Data centers account for what, 1–2% of global electricity demand? Comparable to the entire airline industry. And projections suggest it could reach 8% of U.S. energy usage by 2030.
8%? That's massive.
It is. Training a single large AI model can emit as much carbon as 5 gasoline-powered cars over their entire lifetimes.
Wow.
And the cooling of these centers requires vast quantities of fresh water, screening local supplies. Plus, the hardware itself needs critical minerals, leading to environmental impact and a growing electronic waste problem.
Okay, so that's a considerable cost,
Yeah.
a hidden cost, almost. But then there's the other side of the paradox. AI's potential to drive systemic efficiencies.
Exactly. This considerable environmental cost must be weighed against AI's potential to drive those efficiencies. AI can optimize energy grids to reduce waste, make agriculture more efficient to decrease water and chemical use, streamline logistics to cut fuel consumption, enable a circular economy.
All the things we just talked about.
Right. AI-driven predictive maintenance, for example, can improve energy efficiency by up to 20%. In some industries, AI has helped reduce energy use by up to 60%.
So the net environmental impact of AI isn't predetermined. It really requires a conscious and strategic effort towards sustainable AI.
Absolutely. Developing more computationally efficient algorithms, designing energy-efficient hardware, powering data centers with 100% renewable energy. It's a proactive choice we have to make.
And beyond the environmental, there are significant socioeconomic and geopolitical implications to consider.
Yeah, this is huge. A major one is workforce disruption and transition. AI-driven automation will undeniably lead to job displacement in traditional industries.
Like the autonomous trucks in mines.
Exactly. Autonomous vehicles replacing truck drivers in mines, or AI taking over certain data analysis roles. This isn't just a challenge, it's an imperative for proactive, just transition policies. Meaning massive investment in retraining and upskilling programs for new roles like AI system maintenance or remote operations management. We need pathways for people.
Right. And then there's the global competitive landscape. The high capital investment and specialized expertise required for advanced AI systems. Well, it could concentrate technological capability and therefore power in a few advanced countries and large corporations.
Creating a new kind of digital divide or resource divide.
Yeah, a new form of resource inequality where those with superior AI capabilities have a decisive advantage in discovering, extracting, and controlling natural resources.
And that leads directly to geopolitical strategy. Control of essential resources has always been a cornerstone of geopolitics, right?
Yeah.
AI adds a whole new layer.
How so?
The race to build AI data centers creates pressure on national energy grids and shapes international policy. Furthermore, AI systems managing critical infrastructure power grids, pipelines become high-value targets for cyber attacks. Their security becomes a matter of national security.
Okay, so these are profound challenges. How do we navigate them? How do we harness the benefits of AI while effectively mitigating these risks? The material offers a clear set of recommendations for different stakeholders.
It really demands a coordinated approach. For policymakers and regulators, it means things like establishing international data standards, promoting interoperability, ensuring AI isn't biased. They also need to mandate transparency and explainability that XAI we talked about for AI systems in critical public infrastructure. Decisions need to be auditable and accountable.
And crucially, they should incentivize sustainable AI through tax credits, grants, promoting renewable energy for data centers, and funding those just transition programs for workers in affected industries.
Absolutely. For industry leaders, the imperative is to prioritize robust data governance. Treat data as a strategic asset with accurate labeling infrastructure.
Get the data right first.
Exactly. And they must champion human-in-the-loop systems. Design AI to augment human expertise, using XAI as the primary interface for collaboration. Don't just replace, enhance.
Makes sense.
Investing in workforce development by partnering with educational institutions to create tailored training programs is also critical.
Absolutely. And they should adopt a life cycle approach to sustainability, accounting for the full environmental footprint of AI projects. Finally, for technologists and researchers.
Yeah, for us, the focus should be on efficiency and interpretability, pursuing more computationally efficient models, inherently interpretable ones.
Less energy-hungry AI.
Right. And proactively ensure fairness and reliability by curating diverse training data sets and thoroughly evaluating algorithms for bias. But perhaps most importantly, foster interdisciplinary collaboration. Break down the silos between computer science and domain sciences like geology, ecology.
Get the computer scientists talking to the geologists.
Exactly. The most impactful solutions invariably emerge from that deep collaboration.
Wow. What a deep dive. We've really unpacked how AI, through its sophisticated pattern recognition, prediction, and now explanation capabilities, is fundamentally reshaping the strategic management of essential natural resources. From the oil in the ground to the electricity powering your home. And we've seen how these same core principles extend to seemingly unrelated domains, from predicting human economic behavior to optimizing the global food supply chain.
And while the potential is immense, as you said, we've also laid bare the profound challenges. AI's own environmental footprint, the potential for socioeconomic disruption, new geopolitical complexities.
Yeah.
Realizing AI's promise for a more secure and sustainable future depends entirely on a deliberate, strategic, and, frankly, thoughtfully grounded approach. It's about ensuring these systems are transparent, that their benefits are shared broadly, and that their contributions to sustainability truly outweigh their own costs.
A critical balancing act. So as you reflect on all this, consider this provocative thought. Given AI's unparalleled ability to discern complex patterns in vast data sets, from geological formations to human decisions, what hidden structures or previously unanswerable questions in your own life or your own area of interest might it help you illuminate or optimize?
This is DigitView.